Dear students, welcome to the knowledge series. Here under the course EC407 Computer Communication, we are going to discuss in the area of routing algorithm. As we have gone through my earlier video series where I have discussed about the routing. Routing is the process of deciding where to send a received packet. That is from the source to destinations, how the packet has to route. And this is coming under the network layer, and it's a software that is responsible for deciding the output line to transmit any incoming packet, and it is referred as a routing algorithms. So yesterday, with respect to this routing algorithms, we have seen a routing protocol. Under the routing protocols, there are different types of routing protocols being shown. There are two sections. Is there one is the intra-domain sections, another is the inter-domain sections. In the intra-domain section is nothing but a interior gateways, and the inter-domain is nothing but a exterior gateways. So in the inter-domain, we are seeing that there is a two type is there. One is a distance vector, another is a link state, and in the inter-domain there is a path vector is there. So we are going to see the distance vector in this segment of discussions. Now, to understand this inter-domain sections with respect to the distance vector, here it is being shown a Bellman Ford algorithms. Bellman Ford algorithms help us to find the shortest distance from a vertex to all other vertex of a weighted graph. If you try to see this figure, every nodal point is nothing but a vertex, and this is nothing but a link which is assigned with a specific weight. You can consider this one like a person is traveling from this vertex to this vertex, or this node to this node, or this source to this destinations. So assume that it takes a certain weight or a certain time period. Like that you can assume. So like that, a Bellman Ford algorithms is trying to see that from the source to destination, if it has to move, which is the best possible path, whether it has to take U, W, S, T, V, Z, or U, V, X, Z, or U, V, Y, Z. All these things contributes to identify the best possible path from the source to destination, so that the packet can be delivered without leading to any other form of a network congestions. It is almost all similar to Dijkstra's algorithms, but it can work the graph in which edge can have a negative weights. That means Dijkstra's algorithms, it works with the edge weight that is a positive distance, whereas Bellman Ford works with a negative distance as well. That means it can have a positive as well as a negative distance. Now if you try to see here, there are two things you can see. It defines the distance at each node X. That means at every point of the node you can find it will able to find the neighboring distance. Just adjust. Say take example U. The neighboring is a V, W. X neighboring is a U, Z. So that is what it is being denoted as a D suffix X of Y in a bracket Y. So the cost of a least cost path from X to Y. So that is what we defines. Some another is that you can see it may also define with respect to another notations Cx of V. So actually this is known as a cost of the neighboring, and this is known as the least cost estimate of the neighboring. Now another point is that update the distance based on the neighbor. The first part is that it is identifying the distance of each neighbor and its cost. Another parameter is that it tries to update. How it tries to update? It tries to update based on finding the minimum distance between the neighboring nodes distance as well as the cost with respect to the distance it is taking as an intermediate node. Say for example, you can take an example like this, x to u. So x knows the neighboring distance v. Yes, u knows the neighboring distance v. U knows the neighboring distance w. So v to x it is not aware. W to x is also not aware. So if once this one is known and once this one is known, and by knowing these cost functions and these cost functions, we can try to update the table that it is being maintained at individual nodal points, and thereby it will try to find the best possible way so that the distance can be able to identify in a best possible way, or we can say that how it can able to find the shortest distance. So the Bellman Ford algorithms it is being having a set of steps, and this Bellman Ford algorithm is going to solve the distance vector routing. So we can take this one under the class of a distance vector routing. However, before going to the distance vector, let me explain about this Bellman Ford algorithms. So as you can see here, the Bellman Ford algorithms it has steps. List down the edges of the graph. That means there are several vertex points is there and several edges are there. So this can be done easily if the graph is having a adjacent list. So that's why if A is having a list of B, automatically B will be having a list of D. So A can able to know what is the distance between B and D. If A knows C and C knows D, A will able to know what the C will be having, and that is the distance between C to D. By seeing the table of the C, A will know about the C's neighbor's distance. So that is what we say, list down the edges of the graph. Next is calculate the number of iterations, that is with V minus 1. That means a number of iterations will be equal to the number of vertices. So that means if you are having a vertices, here it is 4, so 4 minus 1, that means that is 3 iterations, because the shortest distance edges can be adjusted with V minus times at a maximum. That is what we can able to do. The third one, you can start with the arbitrary vertex and assign a minimum distance to 0. That means if you are starting from here at A, so you can consider its distance is equal to 0 because it is starting from A. And rest all other nodes with respect to the vertices you can assign as infinite. This is infinite, this is infinite, this is infinite. So all other nodes should be assigned infinite, since we are exaggerating the actual distance with respect from the A. Next is that if each iterations update the distance for each edge, and if the new distance is smaller than the one assigned before, the distance of each node will be cumulative distance from the starting node to this particular node. That means if you are let us take this is you start from here and you have found that some update here, and finally you found the destination node. So if you find these are cumulative, it is keep on adding, and this is also cumulative, it is keep on adding. So you will be seeing that by doing a cumulative adding, or by adding cumulative adding, you will find a cost function, and based on that you will be able to know among these two cost functions and with respect to its neighboring, which is the smallest, and thereby you can able to decide. Consider all the iterations to make sure that all possible path. That means we need to consider all the iteration and to make sure that all possible paths are considered, and by doing this we can end up to the shortest distance. So that is what it means here. Let's see one example which is being shown here. Now here in the Bellman Ford algorithm example, as you have seen this similar figure where this the weighted direct graph is being shown. It is a graph which is being shown, direct graph, and with the vertices, and in between the vertices the edges is having its own weight. So that is what the list of all edges, A to B, A to C, C to D, B to D. That is what it is being shown here. Now what it is shown, number of vertex iteration is equal to vertex minus 1. So that is, there are 4 vertices, so 4 minus 1 is equal to 3. That is total number of iterations. So that is what we are going to see in this case for solving this one. So let us take the first iteration here. Now in the first iterations, what we are doing is that it is the same figure, but the only changes as compared to this one is that we are initializing the vertex at the initial vertex, starting vertex as 0, and all other vertex is having a infinite points. So that is what we have stated. You start with the arbit. You should start with assigning a minimum distance for the initial point as 0, and all other nodes you should maintain as a infinites. So or you can assign a infinite values, so that you can see A is equal to A is assigned 0, B infinite, C infinite, D infinite. Initialize mark the starting point with 0 and other points with infinite. The next. Now here we go to the second, we go with the iterations. Now once we try to see that when we go, we are going to select that what are the two nodes, that is CD, BD, AC, AB. That is what it is written iterations one. In the first iterations, you can try to see that C to D. So that is what it is being shown. It has been shown infinite and with respect to 3. If you take BD, it is infinite and minus 3. If you take AC, it is 0 and 2 plus 2. And if it is AB, it is 0 and plus 1. So this is the first iterations one. Now if you go to the second iteration, you can try to see that in the second iterations level, you will be able to find the B is equal to what is the next case? A is equal to 3 plus 2. That is what is 3 here? This is 3 here. That what is, you can see here, it was minus 3, and now it has going to update it. Let us see how it is going to update it. If you try to see here, 0 and 1 it remains same, 0 and 2 it has remained same. Here it has changed to in the case of a B and D, in case of a B and D, it is showing with respect to -2, because here it is 1, here it is -3. So A to D, how much it is going to becomes? It is 3. That is 1 and -3. That is 1 plus of -3 is equal to -2. That means A will know that its distance up to D is -2. That means this point, it is going for a corrections with respect to this case. So that's how you can see in the first case what we have seen, that every nodal points is infinite. So this infinite has updated to 1 and -3 is remaining, because when we take the case with respect to B and D value A is not aware. So once the D value was aware with respect to 0, so A will try to identify what is the distance from here to here. So that is what we are going to see. So thereby D is updated to -2. Now the next point which you try to see in this particular case is nothing but, here you will find that 3 and 2. So what is 3 here? 3 is here. So 2 plus 3, 5. So this is what we can see here, 2 plus 3. So earlier with respect to C and D it was given as a 3 and infinite. So that was stated. Now here what you are going to see, this infinite is equal to 3 and this is equal to 2. So this value of 2 which was updated between the A and C, that has been aware with respect to this one. So that means 2 plus 3 is 5. Now here in this case, what 1 plus -3 is -2. So D will able to decides that -2 2 and 5. So among this one the minimum value is equal to 2, and thereby the D will stop the iterations. In the third iterations the D will store. So in these sections of the iterations, all the distance will remains the same. So this is what we can see. So in the first iterations what we have seen, 0 and 1, with respect to AB, with respect to AC it is 0 and 2, and with respect to BD it is infinite, because the previous case was infinite and -3, and in this case in CD it was infinite and 3. In the second case, second iterations, these two remains same, but A will be aware that with respect to BD, the distance how it has to calculate. Thereby in the second iterations the B will be putting as 1 here. So 1 and -3 it is -2, and here in the second iteration 2 is assigned to C, because earlier it was infinite. So 2 plus 3 is 5. Among these two, the D knows that 2 and 5, so -2 and plus 5, -2 is small, so thereby D will be upgraded with -2. In the third iterations, the same figure it is assigned and keep it as same, and thereby it will confirm that in the third iterations that this is the appropriate shortest distance. Thereby if you have every nodal point vertex is assigned with the cost functions, thereby it will able to choose this particular path to reach to the destinations. Now we go to the distance vector routing. So what exactly the distance vector routing it shows? Now a distance vector routing, or DVR we can say in short, it is one of the routing protocol, and in this protocol the router informs the neighbor on the topological change. That means, as we can see here in the previous, every nodes has a neighbor, and this neighbor will be informing to the previous nodes about the topological change. And this is like a Bellman Ford algorithms and Ford Fulkerson algorithms forms of that is to calculate the path. And the neighbors, when we talk about a neighbor, these are routers that shares the link under the routing protocols. And every router is aware about what are the network addresses, from where it is coming and where it is routing. Everything is known to that particular router, and this router is uses the distance vector routing, or so that based on that distance vector routing algorithms, router will able to do the necessary decisions. Otherwise, the router uses the distance vector routing will never aware about how the topology changes and how it has to move the particular packet. Otherwise, router will move the packet randomly, and thereby it may not be a shortest distance, rather it will be taking a lot of time period to move, and thereby the traffic may get congestions and the related problems may arise. So let's see the distance vector algorithms. Now if you see across this particular algorithm, a router transmit its distance vector to each neighbors in a routing packets. That means every node is going to identify its neighbor, and it is going to transmit the distance vector. That is what we see in here. Initially it was infinite. After one iteration it has updated to 1. That is what exactly it means. Each router receives and saves the most recently received distance vector from each of its neighbors. That means the router receives and saves the distance vector informations from its neighbor, and the router calculates its distance vector when it receives the distance vector from its neighbor, that is 1 point, and it contains the different informations than before. That means it is updating its information, and it discovers the link of the neighbor has gone down. That is what you can see. Earlier it was infinite, and this d has come to -2 because of the update. That's the thing, is that because this neighbor knows between b and d is -3, but it does not know what is the information between a and b. But every time when it updates, this particular changes observes. The DV calculation is based on minimizing the cost of each destinations. So the cost, when we say this is a cost 1 and -3, 2 and 3, so the nodes should try to see what is the minimum cost it can able to occupy. So here dx of bracket y, that means estimate the least count from x to y, that is the distance, and c x of v. X of v is for the neighbor. The node x know the cost of each neighbor. That means if you try to see here, after the first iterations, a knows what is this cost and a knows what is this cost. So since a will be aware about after first iterations, after the first iterations, a will be trying to know the information. Thereby in the second iteration it is going to update it. Now you may if you try to see how it is going to update this particular informations, so the best way to understand this one is that if you try to see across this figure, this was infinite, this was infinite, this was infinite. So after first iteration this has occupied these two values 1 and 2. So when 1 and 2 is occupied here, automatically in the second iteration this 1 and -3 is here, and 2 and 3 it is here. So that is what I mean to say about the cost function. So this 3 is a cost function between c and d. B and D is this is the cost functions. So that has that cost functions in the first iteration it was not known, but in the second iterations the cost functions has automatically appeared, and thereby it tries to update with respect to the second iterations. dx of y such that y belongs to a number of nodes. That is a number of nodes that maintains the vectors. So that is that is with respect to the selection of the shortest distance. The node x also maintains its neighbor distance, and for each neighbor v, x maintain dv is equal to dv of y is such that y belongs to n. So that is what how the x maintains the the neighboring distance is being defined with respect to dx of dv of y. So dv of y here dx, so dx of y, and this is with respect to the neighbor. Here this is vector from the starting to the neighbor. Now here you can note that from time to time each node sends its own distance vector estimated to its neighbor, and when the node x receives a new dv estimate from its neighbor v, it saves the v distance vector and it updates its own dv using a BF equations. That is what we have seen. When the node x receives a new dv estimate, and then in that case from its neighbor, then it saves the neighboring distance vector in its own table, and thereby it will updates the dv using a BF equations. So BF equations what we are seeing here in this case is being shown, but what we are going to see here, it is in a different form. Dxy, what is dxy? Estimate the least count from a x to y, that is the minimum distance between the x and the neighboring node plus the distance between x and y, and also the distance between y and the neighboring node. Now what exactly this particular statement it indicates? That means assume that there is a node A, there is a node B, there is a node C, or you can take this is x, this is v, and this is y. So I know this node, I know this node, but I do not know this node. So this node, when we try to express, that is what we say dvy, dv and y. But with respect to this, I know dxy, and I know the cost function of dxv. So here we take the x of y comma v of y, that is neighboring to the y, and the cost functions between the x and the neighboring node. If we can sum this one, and if we compare with this one, whichever is minimum, that is what we consider as the shortest distance, that is x to y. So that that is what we say least count y with respect to the source to the destination. Now to understand this one, let's see the examples. Thereby you will be getting a more clarity about the particular distance vector routing algorithm. Now you try to see here in this example, there is a 3 nodes is being shown in this particular example. So x, this is x, y, and z. Now here if you try to see that these three are the routers, and each router have its own routing table. This is the routing table of each router, because you know that every router maintain its own table, that is to maintain the informations, the node which is coming and where it has to go, those informations. So here every routing table contain a distance to the destination node. Now considering a node x, this node x will be sharing information with y. So you can see x to y, what it is showing, no, first is x to x. The starting node x to x is a 0 distance. X to y, it is 1. And x to z, this is what distance? It is 5. So it is updated in the in this particular table with respect to the x scenario. Now if you try to see, this is representing in terms of a vector. So we can represent in terms of a vector. This goes to this, 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 this goes to this. So this is known as adjacent vector represent, and this is a link cost, and these are nothing but a router vertexes. Now when you see the y at that particular instant during that iterations, y will also maintain its own distance vectors and thereby update its table. Y to x, it is 1. Y to y itself is 0. Y to z, it is 2. Now this table has come for y. Z will maintain its table. Z to x is 5. Z to y, it is 2. And z to z, it is 0. So what you can see, that one, all these informations has arrived at the each neighboring nodes, and thereby every nodes will exchange its information and update its values. So let's go to the second figures. Now let us see the second figure here. Now when you try to see this figure, now x will take the y values. What is that? 1, 0 and 2. So it will put 1, 0 and 2 here. Now when the 2 comes over here, so automatically you can see that what exactly the x to z, it was x to z was 5. Now x to y and y to z, what it is? Now actually x to y and y to z, it is nothing but 1 plus 2 is 3. That is x, that is y to x is 1, and y to z is what? 2. So 1 plus 2 is 3. So automatically this x and the new form of x, that is between the 5 and 3, it will try to find that the 3 is the appropriate value, because that is the short minimum value the table should maintain. So the x will replace the z with respect to the 3 based on the cost functions values or the cost links values. So the previous y has been replaced by, this was 5, this was replaced by 3. Now in the next iterations, you can try to see here that this was that things 5 in that same iteration, it was that thing 5 to 0. So 5 to 0 was put here, 5 to 0. So when it is 5 to 0, again x has verified. X to z is what? It is 3. But here x to z is showing 5. So it will replace that 5 by 3, and it become 3 to 0. So when you try to see the final routing table, you can try to see that 0, 1, 3, 1, 0, 2, 3, 2, 0, 0, 1, 3, 1, 0, 2, 3, 2, 0, 0, 1, 3, 1, 0, 2, 3, 2, 0. This is what the final update. This is known as the distance vector routing. Now by seeing this one, what is the advantage? You can say it is the simplest for to configure and maintain the link state routing. So and maintain then a link state, because link state is another form of a routing. So if you see that distance vector is a very simple to configure. Now what is the disadvantage is that this distance vector routing is not much faster. It is a slower form, slower to converge to find the solutions, and it has a risk to count when there is a bigger network, because count to infinite problem exists. And there is also a problem is that every time the router is exchanging the information, so that means it is broadcasting its table informations, so that needs a bandwidth. So there are a lot of bandwidth wastage due to the broadcast. So this creates more traffic congestions because of the number of hop exists between the node to node. So hop means sometime we have to we have to avoid certain nodes, thereby the packet can able to switch from a respective node that can define or that can able to derive a shortest distance. So the hop count take place in a periodic basis, and that I have discussed about the hop in my previous video series. And if the topology changes, thereby the number of hop will also corresponding need to update in that table, thereby the bandwidth wastage will keep on increase. And for a large network distance vector routing, this particular routing results in a larger routing tables. So this may leads a congestion, particularly in the wide area network. And you have to understand the distance vector routing, it uses a connectionless protocol, that is a UDP, for transportations. So this is what we have seen in the case with respect to the vector distance vector routing. So I believe that you are now aware about this particular routing algorithms, how the Bellman Ford algorithm is being used to solve this distance vector algorithms using a node-to-node updates. Now we go with the next discussions on the link state routing algorithms. Now what exactly this link state routing algorithms means and how it has to solve. Now when we as you have seen the vector distance vector routing algorithms, there it was updating its own node point and as well as its neighboring point. But in the link state, what we give stress is that this type of a routing, it is basically a second family of a intra-domain routing protocol. So when we talk about intra-domain routing algorithms, you have to understand it is a interior gateway protocols. And unlike the distance vector routing protocol, the link state routing protocol do not share routing and it does not do a rechargeability. That means just like in the vector case, we are passing the routing informations. There was a broadcast. So that scenario is not coming in the link state. So the informations in the router running in the link state protocol shares the routing informations only with the neighbor, not to the all other nodes. And to discover the neighbor, the link state uses a special protocols, and in that we use as a hello protocols. So however it again it uses the same router calculation, and where it applies the Dijkstra's algorithms on the graphs for calculating. So what is the procedure is that after discovering all the neighbors, the link state protocols created 3 separate tables. One of the table, it keeps tracks of the neighbors, and another one, it tried to see that how the topology changes, and another third one, it is used for the routing tables. So that is, one is the information of neighbor, another is how the topology changes, another is how the node has to transmit from the source to destinations. So here also we will be using some notation like Cij. When I say Cij is nothing but the link cost from a node I to j. that is if the node I and j are not directly linked, then we say Cij is infinite. Otherwise Cij will be having some value. Then we will be using a dv. It defines the cost of the path from the source node to the destination node. So if I say d of x, small x of v, the same thing, x to v distance or the cost of the path from the that particular node to the neighboring node. PV means it defines the previous nodes from the neighboring nodes. So that is the cost path from the path from that particular source which is a neighboring v to the previous node. And n means the total number of nodes available in the networks. So that is what we try to see in this particular point of discussions. So we will talk about these algorithms with respect to the one of the numerical problem. So let us see how this particular numerical problem is being applied to understand this example. So we will be seeing this example based on the problem. As you can see, the network is being shown here. Now here, if you try to see, there are 6 nodes are there. So in these 6 nodes, the algorithms, if you initialize, then we write the n is equal to a, and a is basically the root nodes. That is what we see. We from wherever, if it start from here, then it is a root node, and all node will be having a v. That means every node will be adjacent to the previous node. So we can say if v is adjacent to e, then what we are going to do, we are going to find a distance dv, that is the cost function from the source to the neighboring node. Else if that particular cost function is not direct, then it is considered as a infinite. So that is what we see. That is the first part. The second part is that it will go into a loop. In the loop, what is that? It is going to find a value of w, and w is nothing but the previous least values or the minimum value. So if w is not in the node, then dw will be in the minimum, and we have to keep on adding that w as per the number of nodes, that is n minus 1, and we will update the dv, that is distance of the v to the neighboring nodes distance, and that one, once we complete, then we try to find that and every time we will find the dv, that is the minimum of the previous minimum nodes plus the current node position. Suppose if you are taking b d, that is the current node position, then the previous small nodes which is having a minimum distance, and also its cost functions of the neighboring nodes where it has to terminate, or where the particular destination node exists. That's how we try to do using a Bellman Ford algorithms concept, and this will continue for all the nodes, and finally we concludes. So let's see this problem and how we are going to solve these problems in a very simplified manner. Now the very first step is that you try to see, here we are written a step, here we are written a node A, that is the initial starting node. So that the very first node is this is the first step for initialization. So the currently the least path least path, that is a cost path from A to the directly attached neighbor like a B, C, D, E, F is being shown here. So A to B is 2. So B indicating the neighboring node, distance to B from A. So it is what 2, and what is the previous nodes what is the previous node that is being assigned to B. That is B is indicating here the source, and from with respect to the source B, what is the previous node? It is A. So that is what we say between the A and B. We are defined with respect to direct and with respect to the reverse. So this is what we assigned the link cost, and this is assigned with respect to the vertex of the previous nodes. So that is 2A. Similarly for C, if you try to see the distance between A to C, we cannot take the intermediate node. It is we have to take this one. So it is 5, and what is the previous node of C? It is A. What is the node of the D? A to D is 1, and what is the previous of node D? It is A node, that is A. And what is the node E distance from A? There is no direct link, so it is infinite. So previous is also infinite. And what is about F? It is not a direct, so it is infinite, and from previous it is also infinite. This is step 1. Now we go to step 2. So this step 1, it is being written here, and we try to see the step 2. Now here in this step 2, what we are going to see is that we try to write another n, which is a D. Why? How it has come? If you try to see here, among this link, the minimum cost of every path, if you try to look across at each nodal point with respect to its neighbor, the A to D found to be the smallest one. So that's why we consider that one as the subset values. So that subset subroot vertex we consider as a D. That is why we put as a AD. So now with respect to D we are considering, not with respect to AD. A is over, so now D is coming. So when we are considering D, we are going to write two fact things. One is V and W. When we have to do this this line, we have to write always these two components. One is V is a vertex and W is a subroot that is equal to N. So here subroot is what? Here N is equal to D, because we are comparing with the D. So N is D, and here what is V? We are comparing with this one, B. B is what we define. So D to B. So we are considering D to B. So D to B, we are going to apply the Bellman Ford algorithm concept. D to B is equal to minimum of a dB, comma, then DD plus CDB. Now you may be thinking that how this one has come. Now when we are comparing with dB, so if you try to see what is dB, this is 2. What is DD? DD is indicating with respect to A, that is equal to 1. And what is DB is 2 here in this case, and that is with respect to under this scenario we have got A is the starting node, and here D is the neighboring node, and B is the neighboring node of A. So this ADB is coming. D is here and B. So ADB section is there. So we are writing with respect to DB. That is B. Why we are writing? Why not a DD? Because we are considering this particular node vertex. So DB is equal to minimum of a DB, comma, minimum of a DD, and the cost function of DB. So if you do it 2 and 2, 3, and so minimum is 2. So you can see the minimum value is what it is being shown. It is 2, and currently the shortest path from A to B is 2. So we have seen that where the minimum distance is 2, and with respect to the shortest distance A is equal to also 2. So that is what we have seen. The currently shortest path between the A and B is equal to 2. Now here D is acts as the new subroot conditions only. Now the next, now we are considering the same subroot D and we are considering C, and there again you try to see that A is coming. A is the originating point. That means it is the previous node for the C. So it has to say select from A. So A, D and C is compound. 3 nodes are coming into picture. Now here also if you try to see what we are going to write, A, D of the second factors, D of B. The second factor is considering with respect to the node D of B is equal to minimum of DC and then minimum of DD and minimum of a cost function of CDC. So here one point you have to understand that this factors with respect to this particular scenario, there is a point of suggestions with respect to the for easy understanding. If you see this one, the minimum functions that is being shown every time with respect to dv scenario, if it is showing in this way, here it is showing vd. So it normally it gives the people a confusions with respect to the db. So best way to do this correction is that I can do this particular corrections. You can put this one as in place of a db, you can consider as a dc. So automatically what the minimum of dc, db and cdb. So here it is coming as what 5, and here it is 1 and 3, 4. So between 4 and 5 it is 4. So what you are going to do here in this case, you are going to put it as 4. Now when you put it as 4, here if you try to see what is the intermediate node, here it is T. But here in this case intermediate node, when you take the case with respect to A and D scenario, it was 2A, and in this case the same 2A is going to resides over here. But in this case if you try to see the 4 of D, because your intermediate node is coming as D in this case, so the 5A has transformed to D. These nodes we have to eliminate. The fourth node, it is vertex is what? E, and what is your W? W is same as D, and what was the previous node? It is E. So here this is the E is the infinite point. Now what is the explanations with respect to the distance with it is being defining? It is minimum of DE, because why it is minimum of DE? Just like we are writing minimum of V and minimum of W, that is, and then distance between these two. So similarly minimum of V, minimum of W and distance between these two. So what you find the distance of E, minimum distance, that is E from A is infinite, and what is this with respect to distance D? It is 1. You find it is considered as 1, and what is the distance between these two? It is 1. So 1, 1, it is 2, and 1, and this one is infinite. So that distance you try to see that it is in this particular scenario, that case it remains at the minimum distance as appearing as 2, that is in this particular scenario. So you find that 2 in the case with respect to this particular segment. Now coming to the last one, If you coming to, if you try to see the last particular sections, if you see df, so if you take a df and a d, all are infinite. But if you try to compare with this one, if v is a vertex here, so here if you are taking a v is a vertex here and w is a d, v is a vertex here and w is equal to d, you see v is a vertex here, that is f is a vertex and d, already this is infinite. So that is what it is being shown. So here it is infinite, so it is going to be infinite here. So that is what see in the step 2 scenario. Now coming to the step 3, if you try to see the step 2, it remains same here. Step 3 is what? Again you try to see here, you will find it is among these two, we find this and this is smaller, but let us take this one as a smaller. So we taken that one into considerations. So we will not select this one. And in the previous case this was smaller, so that's why here that is also not being selected collected for the next iterations. So this place is completed. Now if you try to see with respect to the third subroute, it is e to b. So b is the vertex and e is the end point. So that is b is a vertex and e is the end point. So if you try to take the case with respect to that scenario, so we take a distance, so minimum of db, distance with respect to a, minimum of distance e, and the distance between e and b. You know that between cost function between e and b is infinite because there is no direct, that is infinite. D and e is going to be 2. This is 2. This is 2, and db in this case is 2. So that's among this one it comes 2. So that is 2 is been shown, and among the case with respect to the minimum distance of e and with respect to the e with respect to the distance of the b, you find the previous nodal point as 2, so as a. So that is what we shown here. Now coming to the next one, we have a v as c and w as what? E. Why it is e is this one, the subroute. So that is what, every time your subroute remains same, only the nodal point v is keep on changing. That's how you should remember. Now we try to find the minimum distance, that is the minimum of what? dc, then minimum of de, then distance cost functions between these two. So you find that dc is equal to how much it is? It is going to be 4. If it is going to be 4, we should not take 5. This is 1 plus 3, 4. That is what we shown 4. And de, it is going to be how much it is going to be? 2. You can see 1, 2. So that is what. And what is ec? ec is going to be 1. So that is the vertex one. So there we find the ac as 3. Now here if you try to see in this particular case, ac is equal to 3, but here it has come e. Now why it is e? Because e has the point which is coming with respect to e is nothing but the point, this particular nodal point, the subroute point is being used as an intermediate point. So thereby you can see that the shortest distance between a and c, it is through e. A and c, it is through this particular e. So that is how we are taking it into considerations. Now coming to the next is f. If we are taking v as f and w as f, so w as e, because in the previous case w is equal to e. What is the distance, minimum distance with respect to a? It is infinite. And what is d? What is distance of e from the a? It is 2. And what is the e to f? It is also 2. So automatically this everything is going to be infinite. So that's how we see. But in the here it is infinite because here we are going to face D to F, and D to F don't have a direct link. So that's why both were infinite. That's why infinite. So here it has come E. So here E, why it has come? Because of the nodal point of the E. That is how we try to see the case with respect to the third link. Now coming to the fourth, now among this one, which one is small? This one is small. Now fourth link we try to see. In the fourth link, what is going to see? We have to see only this and this. So the B is the subroot, and with respect to C is the V, and W is the B, and here again minimum link, that the minimum link between the C, B and C cos function between C and B. That is what we can try to see here. So minimum distance is 3 with respect to the C is the distance from A. Minimum distance of B with respect to A is 2, and these between B to C is nothing but it is coming as 3. So that if you try 3 plus 2, 5, and 3 is coming 3, 5. That is what we try to see here in this particular case. Now this particular point is completed, and now the next point is A to F. So this is the point. Now here if you try to see, the vertex is what? F, W is B, and we are going to see the distance of V, B, and cos function of F and B. So here also D to F, if you try if you take A to F, it is the first case is infinite. Another case with respect to here it is coming as D to B is distance to B scenario. We will be finding under this particular segment as 2, and here it is infinite. So actually this 2 and infinite becomes infinite. So distance to F is 4. Now you may ask how it is 4. You try to see 1, 1, 2. It is 4. And what is here in this case? The distance up to B, it is 2. And from 2 to B to F, it is not direct link. So that's why cos function is not it is not direct, so infinite. So this 2 and this is infinite, so that is infinite, and this is 4. So 4 and infinite, which is minimum 4. So that is what we see here. It is as a 4 scenario. So that is what we shown here 4. And what is the intermediate node? Intermediate node is just before that one is a E scenario. And finally, in the last scenario, so we take among these two, so this one is small, so that is why we eliminate. And when in the last nodes we find it as, if you try to see in this particular case, F is V, W is C, because this C has come here, and try to see the distance between C and F. So here in this case, distance up to F, we will be getting 4 from A, from C, from the A it is 3, and C to F is nothing but 5. So that is C to F is 5, 4, and this is 4. So we get finally the 4 and 8 minimum is 4, and thereby we find the final things remain same as 4 and F. So this is how the distance vector keeps on updating the table. Now the only disadvantage in this case, because of the heavy traffic, the link state routing, this flooding is a lot of flooding is needed, and this flooding can cause infinite looping problems, and these problems can be solved by using a time to leave field. That means that will be the only issues what we see the disadvantage. Of course, let me summarize this one. The link state routing is that, first of all, you have to find out a node. From this node to the every nodes the its distance, cost functions and also the previous nodes. So that is what we define, and every node is a direct link. It should not be an indirect link. So that is what we try to see. Now when we after doing this one, we try to go with the step 2, where we will be writing a V and a W. V is nothing but the vertex, and the next from the starting node, the next vertex, and what is the intermediate nodes. That is also we are taking, which is comparing with respect to D. So that is what we try to see. All the D will be there, and all the vertex will be keep on changing, because once this is selected as a minimum, only D, C, 1, 2, 3 and 4 has to come into picture. So that is what we show. So we try to find the distance and that distance with respect to in each case is by comparing, and we find it as here as 2 and scenario. The next one, we try to see that in this particular case we find from the 5 it has come to 4. In this case, with respect to the E, it has come to for infinite it has come to 2, and F remains infinite. Now in the third case, again the V keep on changing, and E is the previous minimum nodes, that is the subroot values vertex. So again the same 2A remains. Here it has come with respect to E nodes, and here also comes with respect to E nodes. Finally in the step 4 we are again we went with vertex and W's, that is a C and F, and here it is B, because the previous node was B, which has come small, so that's why it has B has come, and from there we try to find the comparisons, and we found with respect to B, E and E, and finally the final steps we found with respect to the C, because we found the C was the small, and C is compared with the E, so that's why V and W is shown. The distance is nothing but a vertex minimum distance of V, minimum distance of W, plus the cost function of VW. So thereby we found it as the same value 4. So this is how the problems of the link routing link state routing is try to solve these issues. So this complete our 2 point of our discussions. One is we discuss with respect to the distance vector routing, and another is we link state routing. This is a very important from the university perspectives, and you should keep on trying for this various numerical problem, so that it will be easy for you to understand. Thank you.